So the first part, part A for problem 890, is to determine the reversible power output of this turbine. And you know the pressure, temperature, and velocity of the inlet. You know the pressure, the quality, and the velocity at the outlet of the turbine. You know the work that it produces, the work it actually produces is 4.5 megapascal. And you know 220 kilowatts of heat are being lost to the surroundings. Whenever you see a problem like this, always do an energy balance around the system. And so I would do it. So if you do it, we'll draw a control volume here around the turbine, and we've got flow energy coming in, flow energy leaving, there's work leaving, and heat leaving. So if you take the energy balance, and there is no work entering the system, no heat entering, the potential energy at the entrance and the exit are the same, so Z's will fall out. And what we've got, work out, Q out, and you know the velocities at both cases. We can find H1 by noting we've got the temperature and the velocity, so that'll give us H1 by using these two parameters, the temperature and the pressure at state 1 will give us the velocity, or will give us the enthalpy at state 1. And we know the outlet is saturated steam, we know the pressure and the quality of it, and that will allow us to find the enthalpy at the exit stream. The thing that we don't know is the mass flow rate through this system. So m dot is something that we don't know. We do know H1, we know V1, we know H2 and V2. We know the actual work and the heat flowing out of it, so that'll allow us to solve, it'll allow you to solve for m dot. The reason you want m dot is to calculate the reversible work that this system could do. And that's simply the mass flow rate times the rate at which exergy, is entering minus the rate at which exergy is leaving the system. And in words, the idea is that if we could take all of the exergy for the inlet stream, all of its potential to do work, and subtract that, if we could use all of this difference, subtract the exergy of the outlet stream, that'll give us the most amount of work that this device could possibly do. And that only occurs when when exergy, the amount or the rate at which exergy is being destroyed is equal to 0. And you can calculate the reversible work expanding psi1 and psi2. You know the mass flow rate, you know the two enthalpies. T naught is given as 25 degrees C, or 298 Kelvin. We do know the velocities at both points, and we know the potential energy entering and leaving are the same. We can calculate, or you can look up S1 and S2 because you know the pressure and the temperature, the quality of both streams. So we know S1, know S2, and you can now calculate the maximum amount of work this device could do. Part B of the problem asks you to determine the exergy destroyed, the rate at which exergy is being destroyed within the turbine. And the rate at which exergy is being destroyed is simply the rate at which it's being consumed. And the rate at which it's being consumed, you can calculate psi2 and psi1, which we did. The rate at which it is being consumed would be the reversible work that this turbine did. So the turbine, the best it could possibly do, it could utilize all of that exergy, and the reversible work would be the difference in that exergy. So the rate at which exergy is being destroyed is simply the rate at which it's being consumed, or the reversible work leaving the system, minus the actual work that the turbine did. So the turbine operated reversibly, the rate at which exergy was being destroyed would be equal to 0 because work out would equal the reversible amount of work out. So the best this thing could do is if the amount of exergy destroyed was equal to 0. But what you do know, you can calculate the reversible work out, and the actual work out is given to you in the problem, and that'll allow you to calculate the rate at which exergy is being destroyed in the turbine. Part C of the problem says determine the second law efficiency of the turbine. And all this is the ratio of the actual work that the turbine did divided by the reversible work. So just rearranging what we did in Part B, you know the actual work out, you know the reversible work out, so you can calculate the second law efficiency of it. So if the turbine was operating perfectly, if it was operating reversibly, the second law efficiency would be 100%. Finally, Part D asks you to estimate the possible increase in power if the turbine was perfectly insulated. The idea behind this is if we can figure out the enthalpy of the inlet stream and how that compares to the enthalpy of the so-called dead state, And the dead state would be steam at 25 degrees C with a quality of 0. So if we took all of the enthalpy of the inlet stream and reduced that to the dead state, we can calculate the power output that might occur, or that would occur, if we could take all of this stream and reduce it to the dead state. And it's a little bit of hand waving, but we can say the fraction of energy that was actually used, fraction of this enthalpy coming in, is the actual work out, 4.5 megapascal, divided by the mass flow rate times the difference in the inlet enthalpy between that and the dead state. And then you can calculate the rate at which work would be increased would be if this fraction, if the current Q out of 220 kilowatts, if we multiply it by the fraction of work that could have been done with this 220 kilowatts, you can come up with the actual increase in the work.